In this lecture, I'm going to remind you some aspects of linear algebra such as eigenvalues, eigenvectors, Gershgorin theorem, and some other important definitions and theorems. First, I would like to formulate a few definitions that we are going to use in next numerical methods. And first definition is about characteristic polynomial. If A is a square matrix, the characteristic polynomial of matrix A is defined by following equality. Let's say 1. P of lambda, its characteristic polynomial, equals to determinant of the difference between matrix A and product between number lambda and identity matrix, where lambda is eigenvalue of matrix A. And the next definition is exactly about that. If P is the characteristic polynomial of a matrix A, the zeros of P are called eigenvalues or characteristic values of a matrix A. If lambda is an eigenvalue of A and non-zero vector x satisfies equality 2, then x is an eigenvector or characteristic vector of matrix A corresponding to the eigenvalue lambda. And the third definition about spectral radius. The spectral radius ρ of A is defined by the following equality. Let's say 3. ρ of A equals to maximum of absolute value of lambda, where lambda is an eigenvalue of matrix A. First, let me remind you how to calculate the eigenvalues, eigenvectors, and spectral radius for the particular matrix. Let's consider matrix A. By definition 1 from previous slide, in order to find eigenvalues of our matrix A, we should construct characteristic polynomial P. In order to do that, we should just simply deduct lambda from the main diagonal of our matrix A and compute determinant. If we do that, we can get this expression, which is equal to 0, and our eigenvalues will be following. Lambda 1 equals 3, lambda 2 and lambda 3 equal 2. We found eigenvalues. Now let's find eigenvectors. By definition 2 from previous slide, an eigenvector x1 corresponding to the eigenvalue lambda 1 is a solution to the vector matrix equation. Let me write down this equation. A minus lambda 1, which is 3, multiplied on identity matrix, and x1 equals to 0. If we write down it explicitly, we will see this system. Now we should recall how to solve systems of linear equations if this system has linear dependent rows, as in our case, second and third lines. We should recall here the fundamental system. So here we have x1 equals 0, x2 equals x3. Any non-zero value of x3 produces an eigenvector for the eigenvalue lambda 3. For example, let's take x3 equals to 1. As a consequence, x2 also equals 1. And our eigenvector will be x1, 0, 1, 1. This is one example. But at the same time, any eigenvector of A corresponding to lambda equals 3 is a non-zero multiple of x1, also eigenvector for our matrix in this case. Now let's consider second case. Here we have multiple root. And again, we should solve vector matrix equation. Here 2 minus I vector x equals to 0. If we write it down explicitly, we can see that we have 0 row and again linear dependent rows. It means the following. So x1 minus x2 plus 2x3 equals to 0. We have just one equation. Again, in this particular case, we have one basis variable and two arbitrary variables. First, assume that we have x2 basis variable, then x2 we can express as x1 plus 2x3. In this particular case, we have two arbitrary variables, and as a consequence, we have two eigenvectors. So, at the same time, we can pick, let's say, let x1 be 0, then x2 equals 2x3. And our vector will be 0, 2, 1. Also, we can choose differently. We can choose, for example, x2 equals 0. And our vector in this case will be minus 2, 0, 1. What it means? It means that the eigenvectors of matrix A corresponding to the eigenvector lambda 2 and 3 equals to 2 generate plane. And this plane, in more generally, we can express as follows. Let's say x1 minus 2 beta, x2 equals 2 alpha, then x3 will be alpha plus beta. We picked these expressions just for convenience. And our final solution will be x2 plus beta x3 minus 2 beta 2 alpha and alpha plus beta. Finally, by definition 3 from previous slide, our spectral radius of our matrix A is a maximum of absolute value of lambda. In our case, we have maximum between 2 and 3. It's 3. So example solved. We recalled how to compute eigenvalues and eigenvectors of matrix A. In reality, to calculate roots of characteristic polynomial is a difficult procedure, and find the determinant of matrix is computationally expensive. Also, we should remember that iterative methods for solving linear system will converge only if all eigenvalues associated with this system have magnitude less than 1. In this lecture, I'll show you a method which doesn't require us to know the exact values of the eigenvalues. Instead, it requires only to know the region of a complex plane in which they lie. This result was obtained by Soviet mathematician Semyon Gershgorin, who worked in the middle of the 20th century in Leningrad Technological Institute. Let's formulate his theorem. Let A be an n by n matrix and capital R, I, be the circle in the complex plane with center small a with index I, and radius small r, that is symbolically can be written as follows. The eigenvalues of matrix A are contained within the union of these circles. Moreover, the union of any k of the circles that do not intersect the remaining n minus k contains precisely k of the eigenvalues, counting multiplicities. In our case, just to clarify that union of the circles, this is the region where all our eigenvalues contained. I am not going to prove the entire theorem. I will show you how to prove only the first part. If you are interested in complete proof, I would suggest you to read the book Varka, which calls Gershgorin and his circles. Suppose that lambda is an eigenvalue of matrix A with associated eigenvector x. Also assume that L infinity norm of vector x equals to 1. Just to remind you what the L infinity norm is, L infinity norm equals to maximum of absolute value of all elements of vector x. Since x is eigenvector of our matrix A, we can write down the vector form as follows by definition of eigenvector. As a consequence, the equivalent component representation will be following. Let's say formula 1. Then let K be an index with the following property, that absolute value of xk equals to 1. As a consequence, our equation 1 we can rewrite as follows. Here I equals to k. Now let's do some calculations. Let's take out case when j equals k from the sum. Then our sum from equation, let's say 2, we can rewrite as follows, where j doesn't equal to k. And term contains j equals k, we just write down separately. Then let's take absolute value from both sides and apply triangle inequality. Just to remind you how it looks like. And here we have sum. So, but by assumption, we have xk, absolute value of xk equals to 1. It means that any xj less or equal to xk and equals 1 for any j between 1 and n. So now we can replace this with xk and with 1, and inequality still holds. And we can write that lambda minus a k less or equal than sum of kj j from 1 to n and j doesn't equal to k. And this proves that this is, we denote it as a small radius. When we have such k that this inequality, let's say 3, holds, which means that our lambda belongs to closed circle with center AKK and radius R, let's say K. First part of the theorem is proved. Now let's solve an example. Determine the Gershgorin circles for the following matrix A and use them to find bounds for the spectral radius of A. So we have matrix A 3 by 3. As a consequence, we have 3 eigenvalues, and hence we should find 3 circles. Based on Gershgorin theorem, circle we can describe as shows formula in the blue box on the right side. Let's compute them. In order to compute R1, we should look at the first row of our matrix A, and center of this first circle will be at point 4. If we look at the picture, it's our R1 circle with center at 4. It's here. And in order to find a radius, we should sum up all elements of the first row, excluding element from the main diagonal. So if we do it, 1 plus 1 gives us 2. Then let's find second circle, R2. We should look at the second row, and center of this circle will be at point 2. So our circle R2 is here. Now, in order to find radius, we should sum up all remaining elements. It's 0 and 1, which means it's 1. And the third circle, it's here, R3. Center at point 9. And again radius, we should sum up all remaining elements. And do not forget, take absolute values of these elements. And we will have 2. So, if we look at the picture here, we can notice that R1 and R2 are disjoint from R3. What it means? It means that there are precisely 2 eigenvalues within union R1, R2. Let me show you. In this region, we have exactly 2 eigenvalues, lambda 1 and lambda 2. As a consequence, lambda 3 is here. Our third circle contains exactly 1 eigenvalue. So, now we are ready to find spectral radius. To be more precise, we are ready to estimate our spectral radius. If you look at the blue box on the left side, we should recall that spectral radius of matrix A equals to the maximum of the absolute value of all eigenvalues of matrix A. So, to get an upper boundary for the spectral radius, we can use precise formula, and if we compute, we can immediately get that spectral radius upper boundary is 11. If we look at the picture again, we can estimate and lower boundary as well. It's 7. So, at the same time, if we compute our eigenvalues precisely, we can get the following numbers. And the precise value of spectral radius, it's here. So, it's inside our estimation. Example is solved. Before we move forward, let me formulate some definitions from linear algebra, what we are going to use later on. First definition is following. Let V1, V2, Vk be a set of vectors. The set is linearly independent if whenever linear combination of these vectors V and certain constants alpha equals to 0 vector, then all alpha equals to 0 for any I between 0 and k. Otherwise, the set of vectors is linearly dependent. Note that any set of vectors containing the 0 vector is linearly dependent. Next theorem is following. Suppose that V1, V2, Vn is a set of n linearly independent vectors in n-dimensional real-valued space. Then, for any x from n-dimensional real-valued space, a unique collection of constant beta 1, beta n exists with the following property. Vector x is a linear combination of these vectors v and constants beta. Before I provide you the proof for this particular theorem, let me formulate another theorem from previous course. And this theorem we will use in our proof. Theorem 3. The following statements are equivalent for any n by n matrix A. The equation Ax has the unique solution x equals to 0. Second statement. System Ax equals to B has a unique solution for any n-dimensional column vector B. Third statement. The matrix A is non-singular, that is, inverse matrix exists. Fourth statement. Determinant of matrix A doesn't equal to 0. And fifth statement. Gaussian elimination with row interchanges can be performed on the system Ax equals to B for any n-dimensional column vector B. Now let's prove theorem 2. Let A be the matrix whose columns are vectors v1, v2, vn. Let's write it down. Vn. So here italic letters v11, v21 and vn1 represent components of, in this case, vector 1. So the set of vectors v is linearly independent if and only if the matrix equation of the following form has the unique solution which is equal to 0. By theorem 3 from previous slide, this is equivalent to the matrix equation of this form having solution for any x from n-dimensional real-valued space. At the same time, this is equivalent to the statement that for any x from n-dimensional real-valued space exists unique collection of constants beta 1, beta 2, beta n such that vector x is a linear combination of vectors v and these constants beta. Theorem is proved. The next definition is following. Any collection of n linearly independent vectors in n-dimensional real-valued space is called a basis for this space. Let me provide you an example. Question number 1. Show that v1, v2 and v3 is a basis for three-dimensional space. And second question, given an arbitrary vector x from three-dimensional space and find beta 1, beta 2 and beta 3 such that vector x can be represented as a linear combination of basis vectors v and collection of constants beta 1, beta 2 and beta 3. Let's start from first question. Let alpha 1, alpha 2 and alpha 3 be numbers such that the linear combination of vectors v and constants alpha equals to 0 vector. By definition of linear independence from previous slide. Let's write down this equation in components. This is our 0 vector. This is vector 1, vector 2 and vector 3. They are given. Then let's perform some calculations and we will get this vector. Now we should find alpha 1, alpha 2 and alpha 3 and see what solution has this system. The only solution for this system is alpha 1 equals alpha 2 equals alpha 3 equals 0. By definition, we have basis in F3. Second question. Second question states that we have arbitrary vector x from three-dimensional space. Let's say that this vector x has components x1, x2 and x3. And we want to find representation for this vector x through the basis vectors v1, v2 and v3. So again, we write down the system using components and perform some simple calculations. This system, let's say system star, is equivalent to this system, where we should find beta 1, beta 2 and beta 3. These are our unknowns. From equations 2 and 3, we immediately can find one of the numbers. Then it's very simple to find the rest values. Beta 3, beta 2 and beta 1. So we showed that our system has a unique solution. Example is solved. This theorem we are going to use when we talk about the power method for approximating eigenvalues. If A is a matrix and lambda 1, lambda k are distinct eigenvalues of matrix A with associated eigenvectors x1, x2, xk, then set of these eigenvectors is a linearly independent set. So, proof of this theorem I leave for you as an exercise, and right now I will solve example. Show that a basis can be formed for R3 using the eigenvectors of the 3 by 3 matrix A, which has the following form. Let's solve it. On slide 3, I showed you how to construct characteristic polynomial for this matrix and how to find eigenvalues and eigenvectors. For this particular matrix, we have eigenvalue lambda 1 equals to 3 and multiple root lambda 2 and lambda 3 equals to 2. And also I showed you how to find eigenvectors. Lambda 1 has just one eigenvector, lambda 2 has two eigenvectors. So right now we are going to check if we can consider this set to be linearly independent. If we recall the definition 5 from previous slides, any collection of n linearly independent vectors in Rn is called a basis for Rn, which immediately implies that we should show that this set of these three eigenvectors is linearly independent. So, this is a definition 4 from previous slide. We should form the system as we did in previous example. And this is alpha 1, alpha 2 and alpha 3, and we should show that there is a unique solution for this system where alpha 1, alpha 2 and alpha 3 equals to 0. So I leave calculations for you, you can check it. So, and based on that, we can conclude that our set of these three eigenvectors is a linearly independent set in R3. So, hence, this is a basis for R3. Let's solve another example. In this example, let's show that no collection of eigenvectors of that 3 by 3 matrix B, which has the following form, can form a basis for R3. Let's solve it. Well, we start our solution from constructed the characteristic polynomial for this matrix, and we find eigenvalues. And as we can see that our eigenvalues exactly the same as we had in previous example. Lambda 1 equals to 3, lambda 2 and lambda 3 equals to 2. So let's consider first case, lambda 1 equals to 3. We construct similar system of equations as we did in previous example in order to find eigenvectors, and from this system we immediately see that x1 and x2 equals to 0 and x3 is arbitrary. And if we set x3 as 1, we can get the first eigenvector, which is this one. Now let's consider lambda equals 2. We construct system of linear equations as in previous case for lambda 2. From this system we can immediately get that x2 and x3 equal to 0 and x1 is arbitrary. By setting x1 to 1, we can get another eigenvector. So now we should recall that we are in R free space, and as a result of our calculations, we were able to obtain two eigenvectors. If we recall now the definition of a basis, which is any collection of n linearly independent vectors in Rn, is called a basis for Rn, which means that we should expect to have three eigenvectors in our particular case, since we deal in three-dimensional space. And since we have just two, this is not sufficient in order to form basis in R3. So we showed that there is no collection of eigenvectors for this particular matrix which can form the basis for R3. Example is solved. Another important definition is following. A set of vectors v1, v2, vn is called orthogonal if the product of transposed ith vector v on jth vector v equals to 0 for each I which doesn't equal to j. If in addition the product of transposed ith vector v on ith vector v equals to 1 for each I between 1 and n, then the set is called orthonormal. So, if we recall the definition of L2 norm, then a set of orthogonal vectors v1, v2, vn is orthonormal if and only if L2 norm equals to 1 for each I between 1 and n. Let's solve an example. Show that vectors v1, v2, v3 form an orthogonal set and use these to determine a set of orthonormal vectors. Well, in order to solve it, we should find the products v1, v2, v1, v3, v2, v3 and show that these products equal to 0 when I doesn't equal to j. So we have components for every vector, which means that if we can write down this product and compute it for first line, we can show that it equals to 0. If we perform the same calculations for second and third line, we also can show that this product also equals to 0. So vectors are orthogonal and form basis for Rn. Now let's compute L2 norm. Just to remind you that L2 norm, what it is, how we can compute it. Xi just components of our vector. So in our particular case, again, if we consider components for vector v1, we have 0, we have 4 squared, it's 16, and 2 squared, it's 4. And you can get 2 square root 5. If you perform similar calculations for v2 and v3, you can get these answers. In order to find orthonormal set of vectors, let's define vectors u1, u2, and u3. U stands usually for unit vector, as a ratio between vectors v1, v2, v3, and their L2 norms, respectively. So we have component for every vectors given, and we proved also that vectors v form an orthogonal set. So if we compute now L2 norm for every vector u1, u2, and u3, we can find out that it equals to 1, and by definition this set is orthonormal set. This is exactly what we want to find. Example is solved.